Hi everyone. Today we're going to look at projectiles that are launched at an angle, but before we do that, let's just rewind and look at our trig a little bit. We have our mnemonic device, SOH-CAH-TOA, which tells us how the magnitudes of each side of a right triangle are related to the trig functions. So remember that the opposite and hypotenuse are related through the sine of theta. The adjacent and hypotenuse are related through the cosine, and the opposite and adjacent sides are related through the tangent of theta. So if we have one of the sides and an angle, we can rearrange those equations to find whichever unknown sides we have. So for example, if we're given a hypotenuse, which often we're going to be given an initial velocity, and we want to break it into the adjacent and opposite sides, the adjacent is just hypotenuse times cosine of the angle, and the opposite side would be hypotenuse times the sine of the angle. We can also, if we have two of the sides, we can also find the angle by doing what's called an inverse trig function. So on your calculator, right above the three trig functions, you have the inverse trig functions. So for example, we know that the tangent of theta is related to the ratio of the opposite to the adjacent side. So tan theta is equal to opposite over adjacent. If I wanted to release theta from the tangent function, I could do what's called an inverse tangent. And that will release theta from the tangent function. But of course, if I do something to the left side of the equation, I also have to do it to the right side as well. So theta is just the inverse tangent of the ratio of the opposite side to the adjacent side. Okay? And if we know two of the component lengths, then we can find the hypotenuse with Pythagorean theorem. So with that in mind, let's take a look at an angled launch projectile. This particular example is a symmetric trajectory. That just means that this object will be launched and will land at the same height. So the initial vertical position and final vertical position are the same. So when we look at two-dimensional projectiles, we know here we have an initial velocity of 50 meters per second. That's a two-dimensional vector, right? And we know that our kinematic equations, they only work in straight lines. They only work in one dimension. So the reason this is a two-dimensional vector, if I draw the origin of a coordinate system where at the base of that vector, of course, this 50 meter per second at 60 degrees, it's in the first quadrant. It's not on the x-axis, it's not on the y-axis, so it's two-dimensional. So what I'm going to do with this vector is I'm going to break it into a horizontal part, so that's the horizontal component, and a vertical part, or the vertical component. And the reason I'm doing that is I know that when this object is launched, after it leaves the launcher or after the ball is thrown, the only thing that's going to affect that object is gravity. And the acceleration due to gravity is going to be 10 meters per second squared, pointing straight down. So that acceleration can only affect the vertical motion of the object. The horizontal motion will be unaffected because gravity is just pointing straight down. So I'm breaking this two-dimensional motion into two separate one-dimensional motions that I'm already very familiar with. For example, in the horizontal direction, since there's no acceleration, that's just a constant velocity problem. In the vertical direction, since the acceleration is that due to gravity, that's just a free fall problem. So I've got these two separate problems that I'm comfortable with, and then I can resolve them back together to create what's happening in the real world. In the real world, this object is moving in two dimensions. Okay? So what I'm going to look for is any of the kinematic variables that I'm able to come up with from the very beginning. And I'll see if I have at least three of them so that my kinematic equations can start to predict things. Okay? Now you're going to notice that my table is not just x and y or horizontal and vertical. I've broken my vertical up into three different categories, three different columns. For example, I have a v up, which is considering only the upward trajectory of this object. So I'm really looking at just the first half of this motion up to this point right here. Because that particular point is really useful because we know that before the object, as it's going in a positive direction and then it's about to travel in a negative vertical direction, you can't go from a positive velocity to a negative velocity without crossing over zero. So at some point, even if it's for an instant, the vertical velocity of this object is going to be zero. So I'm going to use that to my advantage. That's an additional number that I'm able to use in my kinematic equations. So I've broken this up again into a upward part of the trajectory, and then also you're seeing here the downward part of the trajectory. So let me do that in a different color. So all of my downward part of the trajectory is going to be that. So I'll do this column in green, but I also can look at the entire path. So the entire or total trajectory I'll do in blue. And I'm just going to determine, with the information that I have, can I solve any of those columns, okay? And then horizontal, since I'm looking for the total distance traveled here, this is what they're asking in this question, how far away does it land? I'm just looking at one horizontal column. I want to know how far away does it land. I don't need to break that up into separate parts, okay? So, like with any kinematic problem, I'm going to list my 5 kinematic variables. So I have acceleration, displacement, v initial, v final, and time. Now, I'm going to look at each of those columns and determine if I know any of that information. Well, the first thing I know is that in a projectile or a free fall problem, there is no acceleration in the horizontal direction, or the x direction, so maybe I'll just put an x there. And in the vertical direction, all of the accelerations are going to be -10. They're just gravity, and they point straight down. So I have all the accelerations here are -10 meter per second squared. All right. The other thing that I know is that at the end of the red path, in the upward trajectory, the final velocity in the vertical direction is just 0. Right? That's where it's about to turn over or change directions from positive to negative. So the final velocity on the red path is 0. But that's the same moment in time as the beginning of the downward path. So I could also say that the initial velocity of the downward path is 0 meter per second in the vertical direction. Okay? I think that's all that I know at the moment. I've got my accelerations. I know that my velocity here is 0 in the vertical direction, but I'm going to use this 50 meters per second now. So that's the initial velocity. That's the real speed. What you would see if you were pointing a radar gun at the object. It's going to say it's traveling at 50 meters per second. Well, we can't use that because that's two-dimensional, but we can break it into a horizontal and a vertical part. So to find the horizontal part, or in this case the adjacent side, I'm going to do 50 times the cosine of theta, or 60 degrees. And that is the trig function cosine times hypotenuse is equal to adjacent side. And then the vertical component, or the opposite side, is just hypotenuse times the sine of the angle 60 degrees. So I'll be able to find the initial horizontal and vertical velocity by breaking that 50 meters per second, the real initial velocity, into the x and y components. So I'll do that on a calculator, but before I do, I should check that my calculator is in degrees. So I want to go to mode, and I'll go down here, and I'm going to go from radians to degrees. And second, quit. So to find my horizontal component, it's just 50 cosine of 60 degrees, and close the parentheses. So the initial horizontal velocity is 25. The initial vertical velocity is just 50 times the sine of 60 degrees. And close the parentheses. So the initial vertical velocity is 43.3 meters per second. Okay? So now it's important again to just verify which column this information can go in, because that's how I communicate to the equations where I am on this path. For example, the initial velocity of 43.3 is the beginning of the red path. So on the upward trajectory, I can say that the initial vertical velocity is 43.3 meters per second. And I apologize here, the unit for velocity should just be meters per second. So I want to correct that. On my downward trajectory, the initial velocity is 0 meter per second. Okay? I also want to point out that the beginning of the red path and the beginning of the blue path, which is the total trajectory, is the same moment in time. So the initial velocity of the total vertical column would also be 43.3 meter per second. Okay? The next thing I'm going to look at is if this is symmetric, meaning it starts and ends at the same vertical position, then the vertical displacement for the total path is just 0 meters. And because it's going to have the same upward trajectory time and the same downward trajectory time, I know that when it slams into the ground, that the final vertical velocity is just negative of what the initial was. So on the upward trajectory, the object is slowing down from 43.3 meters per second to 0. And then on the downward trajectory, it's just speeding up from 0 to negative 43.3. So I have the final velocity on the blue path is negative 43.3 meter per second. Again, negative, because at that point it would be pointing down. Okay? So this is identical to an object that was thrown upwards with a velocity of 43.3. If you were to catch it at the same location that you released it from, it would slam into your hand with a speed of 43.3, but it would be traveling in a downward direction. Okay? Let's see if there's any more information that I have. I have the initial horizontal velocity, which was the component of the initial velocity, and that should be 25 meters per second. But because there's no acceleration in the horizontal direction, the final velocity is also 25 meters per second. Again, that's just a constant velocity. Now, I think I have one more piece of information. On the downward vertical trajectory, that end of the green path is the same moment in time as the end of the blue path. So I can also say that the final vertical velocity for the green path is negative 43.3 meter per second. Okay, again, negative because it's pointing downward. Great. So I know that if I have at least 3 of the kinematic variables, typically the kinematic equations are going to work, and I'm going to be able to find other things. I have at least 3 things in every column, which is really great. But the one thing I want to mention is having 0 acceleration actually challenges the kinematic equations a little bit. The only thing that you'll be able to get from the kinematic equations when the acceleration is 0, you're going to be able to verify that V initial is equal to V final. And that's the only thing that's going to come of it. If you look at the first or third kinematic equation and you put in acceleration of 0, you'll see that all that ends up, it shows that V initial equals V final. If you try to do the second kinematic equation, V initial t plus 1/2 at squared, and we see this term go away. Because the acceleration is 0, we end up with displacement equals V initial times t. In the horizontal direction, right now, we don't know either the displacement or the time. So we're kind of stuck here. In the horizontal, we don't have enough information to continue. The only thing we can verify is that the initial and final velocity are the same. So I'm going to look at the other columns. The other columns have enough information to continue on and find time, and then I can use that time in the horizontal direction. At this point, it's really up to you how you want to solve this problem. Do you want to use the red and the green and solve those 2 paths independently? And to get the total time, we could just add the time from the upward trajectory and the time from the downward trajectory. We could add those 2 times together, or you're welcome to use the blue column and find the total time directly. I'm going to show you how to do both just so we have that information, and then we'll go and find that horizontal range or the total horizontal distance traveled. So I'll start with the upward trajectory. Sometimes we just like to have that 0. That can be nice. I want to always start with a kinematic equation, so I'll start with the first one. V final equals V initial plus AT. And I've got A, I've got V initial, I've got V final. So I should be able at this point to solve that for time by subtracting V initial to the other side and then dividing by acceleration. So to get the time for the upward trajectory, I would do final velocity minus initial divided by the acceleration, -10, and I get about 4.33 seconds. Okay? Similarly, if I did the same thing for the downward trajectory, I would do final velocity minus initial divided by acceleration, and you get 4.33 seconds. So at this point, I know that the total flight time is going to be 4.33 plus 4.33. Let's just confirm that with our total total vertical path. If I use the same mechanics here, do final velocity, 43.3 downward, minus the initial velocity, 43.3 upward, and then divided by -10. I should end up with, well, 43.3 minus 43.3, I'm going to get 86.6 divided by -10, and that should be 8.66 seconds. So again, it doesn't matter if you want to be the type of solver who uses the two trajectories independently and adds them together, or the person who just finds the total time. But to find the horizontal range, we're going to use the total time, 8.66. I'm going to bring it over here to the horizontal. That's okay to do with time because time is a scalar value. So in my horizontal direction, I know it takes 8.66 seconds to land. So if I want that horizontal range, and 1/2 AT squared is just 0 because there's no acceleration in the horizontal, I can find out how far this object traveled by doing the initial velocity of 25 times the total time of 8.66. So let's do 25 times 8.66, and this object lands 216.5 meters away. So I've solved the problem as asked. They asked me to find the total range of this projectile. How might this information, though, of the up and the down trajectory, how might it be useful? They could at any time ask us to find the height, or what was the total height or the maximum height of this projectile. So in that particular case, if they wanted to know how high this object traveled, or maybe there was some bar or obstacle that I had to go over, I could find this height by just looking at the vertical displacement on the red path, or the upward trajectory. So I'm going to go ahead and do that now. If I wanted to find the height or the vertical displacement, I would just use the second kinematic equation, v initial t plus 1/2 at squared. So that is, in this column, just the red, the upward trajectory, the initial vertical velocity was 43.3 times the time, which was 4.33 seconds, plus 1/2, or 0.5, times the acceleration, which is in the vertical direction, -10. So times -10, and then times t squared. So I'll use times 4.33 squared. So this object traveled to a height of 93.74 meters. So that's just additional information that I was able to find on this particular problem. So it's up to you what you use. You just want to make sure that as you're going through these columns, that you're communicating to the equations exactly where you are on that trajectory. And we do that with how we choose our final and initial velocity, and also our displacements. Okay, so that was just one example of a symmetric trajectory. We'll get into a lot more examples later, and we'll get lots of practice with this. But hopefully that helps for now, and thanks for watching.